that's very productive, that's not wasteful to time, wasteful to energy, and saving the environment, things like that. So the big problem really that the world has today is every year about 1.35 million people die in just vehicle crashes. This is not just pedestrians, it's really in vehicle crashes. And over 36,000 of, there are over 36,000 road deaths in the US in the year 2019, and that number keeps going up because distracted driving is pretty common. People are, looking at their smartphone when driving, and there's lots of different issues as well. And the economic cost, if you just look at the number of people that die and the kind of, the damage that's caused to everything, the economic cost is well over $1 trillion, just purely because of accidents caused by human error. And in addition to that, just besides the safety problem, there's also more of a congestion problem. Every American typically spends about 99 hours on average on the road doing nothing, right? Just waiting for traffic to clear. And that was the statistic from the year 2019, and it's getting worse. And over $88 billion is just wasted because people are sitting in congestion doing nothing. So that's the cost, right? In terms of accidents and in terms of congestion, that's the cost any economy kind of goes through. One of the companies that looked to solve this problem is what we call Waymo One. Waymo is the Google self-driving car project. They started a company that was an offshoot of this project. And Waymo announced a ride-hailing service in Phoenix, Arizona just last year. And they have been running basically a taxi service in Phoenix City, and many of those taxis are completely driverless. So you can basically pay for a fare and get in and get out wherever you'd like. The vehicle is completely driverless. Waymo has been working on it for many, many years. The technology itself was one of the Google R&D projects, and then later they converted it into a company to actually make it a commercial service. They've run a lot of tests over the years. They've actually driven well over 20 billion miles. Their algorithms have been tested for well over 20 billion miles in a combination of real-world testing and simulated testing. So that's a lot of miles. And well over 20 million of that were in real road conditions in various cities in the US and possibly outside the US as well. So there's a lot of testing that happened on real vehicles with safety drivers in many cases. So in the year 2019 to 2020, they started the whole service in Phoenix where real people can call it like an Uber and get into the vehicle, get down somewhere else. And they've driven about 65,000 miles in that 1 year alone, completely driverless, without any driver inside the vehicle. So that's a lot of miles. On average, it's like about most US drivers would take about 500 years to drive that many miles. So that's a significant number of miles they've driven without any driver whatsoever. So Waymo is now a viable service. They're still in testing phase. They're not completely autonomous yet, but they have many vehicles that are running in one city in a completely autonomous manner. So there's a lot more work to be done to be able to do this in every city around the world and in different scenarios and so on. But this is a very, very good start. This is the first commercial ride-hailing service that's fully autonomous in the world. And then another company called Cruz, which was a startup in San Francisco. It was bought by GM a few years ago, and they were also invested in by Honda. So Cruz, they started their own autonomous vehicle development. They've driven about 2 million miles compared to Waymo's 20 million miles on a real road. Cruz's miles are much, much lower. That's because they're a much smaller company, and they have about 300 vehicles, but most of the testing was done on 30 vehicles. They only started expanding their vehicles now. And their testing, very important here, is instead of Phoenix, which is a relatively simple city in terms of traffic and so on, they tested their vehicles in San Francisco, which is a very complex city. Ups and downs and mountains and real bad traffic and lots of pedestrians. It's a very bad environment. So it's a much tougher environment for autonomous vehicles. So Cruise, they use San Francisco as their testing city, and they've done about 2 million miles. And their algorithms and their experience has been much more complex, maybe possibly more complex than even Waymo's. They introduced this vehicle, what they call the Origin. You can see that there's no front or back to this vehicle. There's no driver's seat. There's no steering wheel. It's purely autonomous. It just picks up passengers, drops them somewhere else. You can clearly see some sensors, lidars. There's a lot of cameras, radars around this vehicle. And the whole idea is there is no longer going to be a driver in this vehicle. This vehicle will be deployed in 2023 in configurations. They may have a safety driver for a little bit, but it's going to be deployed in commercial service in 2023. And Dubai may be the first city where they deploy this. So over the next several years, until 2030, their hope is to be able to launch about 4,000 vehicles, fully autonomous, in Dubai and other cities across the world. And Zoox is another interesting vehicle. When you look at the Zoox vehicle and the Cruz, what you kind of see is that there is a little bit of a difference. The Cruz vehicle, you can see there's some sensor up here in the back, in one side of the vehicle, and that sensor is missing on the other side of the vehicle. So there is effectively a front and a back to the Cruz vehicle. But in the Zoox vehicle, there really isn't one. This is a startup based in San Francisco again, and they've been testing in San Francisco and Las Vegas. They were acquired by Amazon in 2020. And they've been driving. I mean, they're a relatively young company, less than 5 years old, I believe. Actually, they were founded in 2014, but they were mostly in stealth for a while. But you can look at this vehicle. There's no front and back. This vehicle can actually go in either direction by itself. So if a vehicle is autonomous, there's no driver's seat and there's no driver steering wheel. Why do you have directions at all? So it can go in either direction and it can drive up to 120 kilometers per hour, which is pretty fast. And the idea behind this, again, is pick up people, drop them somewhere. You can use it in any ride sharing configuration in any geography. So this is the genre of vehicles, basically what we call robotaxis, right? These are taxis, Uber kind of vehicles. And the whole idea is there will not be a driver anymore. They will be driving people around. You can use it in a small locality, like, picking up people from inside a big campus and dropping them inside the campus itself, like a university campus, or you could do it city to city as well. So different vehicles have different shapes and different configurations, depending on what kind of mission they're going to be running in. So there are many, many different companies, as you could see, Voyage, Baidu having something called Apollo, Zoox, and even the traditional automakers like Mercedes-Benz and even I think GM, Ford, everyone is announcing robotaxi plans. So the idea here is completely autonomous vehicle, moving people, safety, environment friendliness, and avoiding congestion, because people no longer have to do their own driving, usually just sitting one person per car. So that's the robotaxi world. I want to take a break for questions. Feel free to ask questions about this particular part of the presentation, and then we could answer maybe 2 or 3 questions and then move on to the next step.
And there was a question posted in the chat box by Rajagopalan. Computers are prone to hacking. If we automate and compute all the vehicles, it is also at the risk of being hacked. What protective measures are being taken in terms of cybersecurity to prevent Taliban-like terrorists to carry out an attack to Phoenix remotely from Afghanistan itself?
That's a very good question. The interesting answer is it's not easy. I mean, you have billions and billions and billions of smartphones in the world today, and many millions of smart TVs as well. How often do you hear of a hacking story from a smartphone? You don't hear that very often because of 2 things. We do take cybersecurity very seriously. There are sometimes vulnerabilities, but once you find that vulnerability, you can immediately fix it and deploy the fix very fast. And then you kind of learn your lesson. The next design kind of avoids those issues, right? So we've learned a lot from smart device design and having them, with millions and millions of people. So those lessons are all going into designing these smart vehicles. So it's not just for robotaxis or autonomous vehicles, but even general smart cars There have been hacking incidents of people, hackers, ethical hackers getting into actual Chrysler vehicles and things like that by usually getting into the infotainment system through a wireless link and then slowly hacking into the rest of the ECUs. Those issues have been very helpful to find out where the vulnerabilities are in vehicle design. So we've taken that very seriously. We've done a lot of really interesting design work. Is that completely safe? Not yet, but over the next several years, will we make it completely safe? I'm very, very confident, right? Because you today have very complex machines that cannot be hacked because they've kind of iterated through the cybersecurity problem. So cars will get there as well pretty soon.
So there is also another question. The cost of labor is low in India when compared to US. In that case, the autonomous vehicles will be having a much higher capital and operating cost than the current ride hailing cost. Will autonomous ride hailing service ever pick up in India? Also, it will be much difficult to drive in India with the reckless drivers.
Well, I get this question. You wouldn't believe. I do get that question. um, so the well, actually, we have to address it from multiple different perspectives. One is in the US, you don't typically, San Francisco, as I mentioned, is a very complex city. Las Vegas is an even more complex city. Pedestrians just don't even care about vehicles, they just walk anywhere they want. But obviously, nothing even compares close to the complexity of India. But when you think about there are areas where autonomous vehicles would be very valuable. There needs to be some level of government support as well. Yes, autonomy, there's a part of this, the robotaxi world at least, there's a part of it is really the labor cost of the driver. But there's also the element of safety, there's also the element of congestion and things like that, which apply to India as much as they apply to the US. So there is definitely a good, significant gain to be had. But yes, the infrastructure does have to keep up. Autonomous vehicles are effectively not very intelligent, right? They need very clearly marked signals, lanes, and traffic signs, and so on. So they cannot adapt to Indian driving conditions. But you could create a zone, specific zones in bigger cities where you want to reduce congestion. You could possibly create a specific lane for autonomous driving, autonomous vehicles, robotaxis to pick up, or autonomous buses. So that kind of infrastructure support is needed, which is kind of in most cases is available in many US cities. Phoenix is easier. That's why many of these companies are going to Phoenix. So yes, it's not just the vehicle. There's got to be infrastructure matching as well.
So another question from John Knox. Is these technologies available with the Indian manufacturers?
Yes. Jaguar Land Rover, which is essentially Tata, has done a lot in autonomous. There are many startups in Bangalore and beyond that I know of that are working on some part of the autonomous problem. And there's obviously so many companies in Silicon Valley which are owned by Indians that work on this as well. And they are very, very motivated to have this technology kind of branch out into India as well. So yes, it is very much available in India, and it is available to India through companies and entrepreneurs that are of Indian origin.
So another question from Srimati. This is regarding the memory of this autonomous vehicle. How is the high-speed memory being used in the autonomous vehicles? Like how we can determine the capacity, speed of the memory consumption?
So that's an interesting question. These vehicles, it's all about the response time, right? There are so many sensors. Some of these vehicles can have up to 12 cameras, at least 5 lidars, many radars, many other sensors as well potentially, and all that needs to be processed. So you've got to build these computers that are capable of processing all this, and your response time is in the order of milliseconds. So if you see a pedestrian and you need to apply the brake and you're driving at 100 kilometers per hour, it takes a while for the vehicle to brake. And so the response times are extremely critical. So high performance computing includes, high performance memory and storage and all that. So this is a very, very interesting hardware design problem, software design problem, and a mechanical design problem as well. So this is very multidisciplinary. Autonomous driving is not just about computing or software or hardware. It's really very, very multidisciplinary. And you'll see that as we go forward in some of the other slides as well.
Next question is from the faculty, Venkatesan. Please let me know about the challenges in autonomous navigation in the largest population country like India and China.
I will come back to that question as we get into the technology. There
Okay.
are a few slides down. I do have something about the technology. We can go into the next section, and then I can continue the questions in the next.
Yeah, sir.
Okay, so we spoke about robotaxis. That's just one particular application of autonomy. The other problem, which can be a bigger economic problem, is moving freight. If you look at a country like the US, I think the last count, the economy size was more than $14 trillion. Um, Everything moves by trucks. We are not very good at having amazing railways. Everything moves through road, and there's like 304.9 billion miles traveled by trucks moving goods inside the US in 2019. And that number is only going up as the economy goes up. $72 billion worth of freight was moved in that year in the USA alone. So very, very huge, dependency on trucking in the US because of the economy. But then when there is a crash of a truck, there is an average loss of about $70,000 in that particular year, and that cost is also going up. But here's the real problem. When COVID hit and when everyone really needed to lock down, I mean, you cannot stop trucking because goods have to still move around, right? And this industry is perennially, there is a shortage of drivers. So this is always a big problem with, I mean, the shortage of drivers is expected to go up as well. There is a labor shortage, there is a safety problem, and there is definitely a regulation problem as well. Think about a truck driver, they're driving about 2,000 to 3,000 miles a week. Most of the time, they don't even come home. They earn a lot, but they don't even come home. They're pretty much on the road driving around, and there are limitations on how long they can drive and how many hours they can drive together, things like that. That's all mandated by the government. And the shortage is very, very high as well. So how do you solve this problem using autonomy? Turns out it might be a little bit easier to solve that problem than the robotaxi problem, because the robotaxi problem is about the robotaxi has to be able to drive through normal urban streets where there are people, and it has to deal with the same problems that a typical human driver runs into. But trucking may have it a little bit easier. In what sense? Because most of the truck driving in the US happens in the US and Europe as well, happens in expressways, in freeways. And that is basically, there are no signals, there are no pedestrians, there are no stop signs, none of that, right? You're basically maintaining a constant speed from San Francisco to New York. You don't have to take an exit if you don't want to. It's like completely, it's one road without any obstacles. So that gives you an advantage of you could have a human driver drive until your truck gets into a freeway. And then at that point, you engage the autonomy, and the truck keeps driving until it gets to the next exit point, which could be 2,000, 3,000 miles away. And then the human driver takes over, drives it. Because driving in an urban setting, especially a truck this large, is going to be a bigger problem than just turning a robotaxi. So you can break down that problem and say the 2,000, 3,000 miles between San Francisco and New York, the truck can drive autonomously. And the human driver does not have to take a break. They don't have to stop to take a nap. The vehicle can drive itself autonomically, right? So there are many companies focusing on that problem because of the cost of freight and how important freight is, and this whole driver shortage problem as well. TuSimple, which just went public about a month or two ago. They are the first $1 billion unicorn that works in this space, particularly with autonomous trucking, and they're based where I live in San Diego. What they've done is really developed the autonomous algorithms. It's not completely autonomous yet, but the advantage that they claim here is, compared to a human driver, when you drive the truck using an algorithm, you can drive it more fuel efficiently. You can, the braking and acceleration is all much more smooth, much more algorithmic, which means you could save anywhere between 3% and 5% and 10% in fuel alone by having an algorithm drive the truck compared to a human, because the human can, they are more erratic. Even if you don't think you're erratic, the human response is much more erratic. So it can lead to more fuel consumption. So TuSimple used that fuel consumption advantage as the value proposition to say, I can ship freight cheaper because I can save about 10% money. And the 10% is the minimum. And then you can keep saving more if you remove the driver completely from the equation. And they used the Arizona to Texas in the U.S. South specifically. That particular area is one of the most busiest trucking zones in the U.S. So they run trucks in this zone where they move goods, and they also help other trucking companies make their trucks autonomous using the TuSimple technology. So that's one company that's solving the trucking autonomy problem. It's purely about economics. And so TuSimple's claim is you can save up to 10% just from autonomous driving system alone, even if you don't eliminate the driver completely. If you eliminate the driver completely, then you start saving money in the driver wages as well. And that comes to, again, Waymo, which we spoke about a little bit earlier. They developed the Google algorithm for self-driving cars, and they put that into a Robotaxi for taxi service. They've deployed that taxi service in Phoenix. And they also take that same technology. They are now applying it to trucks. And that means the same fuel advantage and also the cost advantage of not having a driver, things like that. So they're kind of reusing that technology in trucks. There's tweaking needed. Of course, the response of a truck is not the same as a Robotaxi, but there's work being done. And Waymo is also doing the same thing. They're working with trucking companies. They're running their own trucks as well. They're running their own shipping service as well. Overall idea is to improve make them fully autonomous, at least with respect to that freeway. So autonomous trucking, many different companies. You can see Mercedes tried this, and other companies. There's a company called Einride. They're making autonomous pods. You don't need a driver, so you don't need a driver cabin. So there's lots of work being done in this space as well. The driving force behind all this is economics. And there's an interesting concept here called platooning. So you don't necessarily have to be fully autonomous, right? You don't necessarily have to drive all trucks without a driver. Why don't we take this approach? There will be one truck in the front. It'll be driven by a human driver. But there could be like even up to 10, 20 trucks behind it. They all effectively communicate over radio, and all the other trucks just autonomously follow the lead truck. So the lead truck is driven by a human, and all other trucks autonomously follow this lead truck. So you're paying one driver, but you're driving 10 or 20 trucks. That reduces the cost significantly. And also the front truck is going to be subject to all the aerodynamic drag, and the rear trucks are not going to be as badly affected by aerodynamic drag, right? So that also reduces fuel consumption for all the trucks. So the more trucks you have, the more money you save. So truck platooning is a very interesting area of development as well. And this is effectively human-driven, except that the trucks in the rear are not human-driven at all. So that's another variation of being able to autonomously drive trucks. With truck platooning, you can save anywhere between 30 and 45% costs for freight trucking in the US. But that's a very, very significant number because trucking is a very low profitability industry to begin with. 1 or 2% profitability difference can actually make the difference between a good business and not good business. So if you can give them a 30 to 45% cost advantage, that's huge from a business perspective. So this is an area where there's like so many startups working, including the big ones like Waymo. So very, very interesting space. You can see that it's completely different from robotaxis. You're not moving people, you're moving lots of goods, big trucks. So the technology is the same, but the dynamics of the vehicle are different. So with that, we'll take another break. More questions.
This was a question asked, challenges in autonomous navigation, your faculty, and by Jayashree. What is the good pretest task for self-supervised lane detection in autonomous driving car?
Did you say pre-test for lane detection?
Or lane detection.
Okay, so I'm not sure I'm answering that question correctly, but let's say, lane detection is a very simple problem, right? It's something that we've many companies have solved, and there's also variations to it. Most of the time, it's usually one or two neural networks that get trained to detect the lanes pretty well, and the lane quality matters, and the quality of these algorithms depend on the lane quality. It's even in the U.S. Even though the infrastructure is pretty good, there are circumstances where the lanes are not clear, or instead of a lane there is a wall, or instead of on top of the lane there's debris, there's just dust and all that stuff. All those problems do exist. So different algorithms have different levels of quality, and there's definitely competition, right? There's no single answer to it. Many different companies are solving those different problems using various techniques. So many different techniques are being used to improve lane keeping, which is basically keeping in the middle of those lanes and continuing to drive for a long time. One of the companies that I spoke to, there's a place called Page Mill Road in Silicon Valley, if some of you have heard about it. It's a very, very windy road. It's one lane, very windy, and most of the time on the right side of the vehicle, there is no lane. It's just pretty much, there's a big cliff on the side. Your vehicle goes over. So it's a very interesting road, and one company that I spoke to actually tests their algorithm on that road. So even without a clear lane marker, that vehicle has to keep to the road, a single lane road. And if you change lanes to the other side, there's vehicles coming at you. So companies use different techniques to test this. At the end of the day, it's really difficult to say which one has a better algorithm.
Next question is from Rajagopalan. We heard autonomous vehicles use a common algorithm called the waypoint algorithm. Are there any other algorithms used and better algorithms used, sir?
Yes, there are many, many different algorithms. So effectively, we'll get into it when we get to the technology. I mean, there's only so many functional blocks in autonomy, and as we just saw, there's different scenarios as well, right? Urban, parking, very dense urban, and also highway. There's different scenarios in which these vehicles run. So companies develop their own techniques, their own algorithms, their own approaches to solving the autonomy problem. And even within robotaxis, each company has a different proprietary approach to it. They don't always publish them, but there's not a single approach they all follow. There's so many different approaches.
So next question from Rohit. Do people are willing to accept this technology?
That is a very, very good question. Not really, not yet. The first time you get into an autonomous vehicle, you're extremely nervous, but you kind of get used to it. It also depends on how good that vehicle is. But psychologically, and this is another, here's the thing, this is not all about engineering. There are studies being done in psychology departments across the world on how to make sure people accept autonomy as a technology. So it's going to take a while for people to get used to this. And there's going to be different problems you'll find. One question that keeps coming up is, I'm in a robotaxi at midnight, and it's in the middle of nowhere, and the vehicle stops. What do I do? I'll panic. So those issues are being studied as well. Those potentials are studied, and the technology solutions for those issues are also being looked at.
So next question is from our faculty, Venkatesan. Please let us know about the risk factor involved in deploying the autonomous bus or the vehicles within the existing public transport network.
Well, it's not a difficult problem. I guess in the US context, a bus is a larger vehicle. That's all it is. It's going to use the same algorithm, same pretty much the same infrastructure, same facilities. But think about the bus is heavier, like a truck is, so the stopping distance is longer. One interesting thing is, for a car to come to a complete stop when it sees a pedestrian, you probably just want to be able to see that pedestrian from about 150 to 200 meters away. But for a truck to come to a complete stop without hitting the pedestrian, it's got to be able to look at them from about 1,000 meters away. So that means, higher resolution camera, better algorithm to be able to detect the person, things like that. So there are variations in the technology, but same thing applies to buses, right? Except that buses can be in an urban setting, they can be much slower. So you can limit the speed, you can limit how, I mean, in what zones it drives, things like that. So that's called geofencing, and that's called the ODD, right? Operational design domain. You design it to run in a certain environment, and it doesn't really work well outside that environment, which is perfectly acceptable for autonomous.
So next question is from Srimati. Do these self-driving cars use only reinforcement learning as you train them based on the environment, or do they also use supervised learning?
They use all kinds of learning. Supervised learning is where most companies started out. That means you have to really annotate all your data and train your algorithm, and it takes, it actually takes very significant investments to do this. And of course, there's a lot of, imagine this. Tesla once joked that I have 300 engineers in the autonomous driving team. 200 of those are just annotating pictures. So that's not where you want to go. But that's the problem. Supervised learning is where we started, and of course we tried other things. And there are now companies doing research on using unsupervised learning, which basically means you don't have to annotate that much data. You can really start using it in a real world. So it's a research area. Where I'm definitely betting on unsupervised learning to reduce all this manual labor. So different approaches are being used by many companies. So we could switch to the next slides, and then we can come back to questions later. Is that all right?
Okay, okay.
Okay. Okay, we spoke about robotaxi, we spoke about trucking. There's another very, most of you will relate to this, last mile delivery. You come out of your house, anywhere in the world, any city, doesn't matter if it's an urban area or a rural area. How many delivery vehicles do you see, be it Amazon or UPS or whatever the company is in your country? How many vehicles do you see? In my neighborhood, when I come out, within a mile of my house, I usually see 5 Amazon delivery trucks. It's huge, right? In terms of number of vehicles on the road, how much gasoline they're burning, how much pollution they're creating, and how much congestion they're creating as well. But for Amazon and all these different delivery companies, it's huge business. They have to do this because their customers want delivery within an hour, within 30 minutes, all that stuff, right? And same goes with pizza. And when you order food from any of these services, you want the food really fast. This delivery being made in the last mile, as in very short distances from a shop or from a facility to a home, $15.05 billion, 15.05 billion deliveries made in 2020. And 2020 was the COVID year, so not much was actually happening. Most people were switching to to deliveries, right? They were not going to shops and things like that. But still, it was kind of a mixed year. And that was the number of deliveries in 2020, 4.9 trillion, which is a pretty big sale number worldwide. And then, of course, most of the transportation cost for delivering something, if I bought something, let's say on Amazon, most of that, 53% of that is really spent on getting it from an Amazon warehouse to my house, not from a factory to the warehouse in the first place. 40% of all the cost savings will come from really autonomy. If you make this autonomous, you're saving about 40% of cost of delivering that product to you. And not to mention the fuel burn and things like that. Amazon recently, last year, they ordered, I think a couple of years ago, they ordered 100,000 electric delivery trucks from a company called Rivian, because they are known as a big polluter, right? Given the number of trucks that are going around the world that are gas trucks. So they are looking to become more electric, and they're also looking to become more autonomous. So now let's look at how companies are solving that problem. By creating a vehicle that's very special for that mission. This company called Neuro, again based in Silicon Valley in the US, they just designed the vehicle completely differently. There are not going to be any people inside the vehicle. It's a smaller vehicle. It's fully autonomous. What's inside that vehicle is just stuff, right? It's probably vegetables, fruits, pizza, food, that sort of stuff. And that means most of the design of any vehicle today it's made stronger so that you protect the human occupants inside the vehicle. So the vehicles are heavier and they're stronger and tougher because you want to make sure if it gets into a crash, you protect what's inside the vehicle. So that means what's outside that vehicle can, bad luck to it, right? It can hit a pedestrian and the pedestrian is going to be hurt. So if you don't have people to save inside this vehicle, you can make this vehicle lighter, not as stronger. It doesn't have to be reinforced. The vehicle can be damaged very badly when it goes and hits something. All you lose is a few pizzas. So the whole vehicle design challenge becomes different. This vehicle can drive very, very slowly on the side of the road. It doesn't have to, go fast and change lanes and things like that. All it can do is really drive at maybe 25 miles per hour, which is the lowest speed limit in the US, and go from a pizza shop to your home, deliver the pizza. And you use a code to open up the door and you take your pizza and it closes. So effectively a robotaxi to deliver products, not people. Neuro launched in Houston. They've been delivering pizzas for Domino's, and they're also delivering groceries in various cities in the US. So it's still in trial, but it's a very interesting concept because now with the reduced costs of delivering products like this, there's so many businesses where just the cost of delivery alone makes that business totally unprofitable, unviable. Now with this, they can actually make more profitable business and more viable businesses. So very interesting concept and very interesting company as well. Same thing with Amazon Scout. Imagine all those Amazon trucks. If they didn't have to drive around taking all these goods, but these little battery charged robots are driving around, taking your product, taking it to your home, and you get to pick it up from the robot, and the robot goes off to deliver another one. So Amazon's been working on this, and they also acquired Zoox and a lot of other autonomous technology companies. So very clearly, their focus is eliminating the human driver as well. Going electric is to reduce the gas wastage, and then going autonomous is to reduce the driver. So overall, the idea is to reduce the cost of delivering a product to a home. So this is a very, very interesting space across the globe. Where it will be beneficial is, again, same thing, right? Where if you reduce the costs low enough, what cannot be a profitable business can become a profitable business. So that's what's making it very attractive. Even small shops, pizza shops, groceries, etc., become much more attractive. And that means you could possibly have very interesting business opportunities as well by using autonomous vehicles for this. So if you think about the number of vehicles in this last mile delivery space as well as in other areas going autonomous over the next 10 plus years, just imagine how much fuel savings are going to come in, how much in terms of the economic impact, making more unique businesses viable, and impact on climate change. Lots of different factors come in, and the impact of these vehicles on the globe, it's going to be huge, very, very huge. It's kind of pretty much unmeasurable at this time. So that's a very, very good opportunity and a very good transformation to the world as well. Okay, now we can jump into the questions, and then I'll go in a little bit more into the technology.
Any questions? So this is a question from Rahul. Sir, do these vehicles are synchronized to avoid areas like heavy snowfall, flood, sandstorm, etc.?
They can do that because they are connected. They can obviously be warned about weather, and these vehicles can be designed to be functional under certain weather conditions. Again, it goes back to that what we call the operational design domain. I can always say my vehicle will only be functional when it's completely sunny. It cannot operate when it's raining or snowing, things like that. And if it's raining, you can obviously send a note to the vehicle saying, wherever you are, just go find a place to park yourself, right? All that is possible because it's connected, it's smart, it can do a lot more, it's more responsive. So there's different technologies that are being developed as well, including remote piloting of the vehicle. Maybe the vehicle cannot autonomously drive itself, but a human can remotely pilot it and bring it back to safety. Things like that are also being possible.
Sir, I have one question. What is the additional cost as well as the maintenance cost for these autonomous vehicles?
That is a very interesting question as well. When Waymo first got into this autonomous business, they were building vehicles. They would buy something like a $35,000 Lexus SUV, and after they make it autonomous with all the computing and all the lidar and everything, it became more like a $250,000 vehicle. So the cost of these computing and sensor, all this equipment, was very, very high. But that's because these are not manufactured at scale, right? These are very unique equipment that was for one or two vehicles. Over a period of time, that cost has come down. LiDARs used to be like $100,000, just one LiDAR. Now there are LiDARs available at $250 or less. And that means you can put more LiDARs and you'll still not spend $100,000. That Cruz origin that we saw, the picture, it is estimated to be about a $50,000 vehicle. So at mass manufacturing volumes, they expect it to be manufactured for 50,000, which is very, very low because today a luxury, a Mercedes car can be 50,000 to manufacture. So they're bringing down the cost significantly.
Another question from Venkatesh. Sir, there are certain places where the network connectivity is poor. How can we operate autonomous cars in those areas?
Autonomous does not need network connectivity, but there are technologies that allow us to take advantage of network connectivity if it is available. So this is, again, there's a little bit of philosophical approaches to this as well. There are some companies that are saying, okay, with 5G, with things like CV2X and DSRC, you can take advantage of all of this, and you can deliver better autonomous features. Great, that's all nice, but there's still, interestingly enough, given how big the US is, and you kind of think communication should be ubiquitous in the US. More than 2/3 of the US really does not have very good network coverage. It's only the urban, really, really dense urban states where you have network coverage. So if you have an autonomous vehicle in the middle of Death Valley or any desert in Arizona and so on, there's not enough coverage in terms of network. So autonomous vehicles need to be able to operate without a network. But if there is a network and there is data connectivity available, obviously it can use more features to operate better. So that's, at the very minimum, you should be able to operate without any network connectivity whatsoever.
Yes, that's all questions.
Great. I can jump into the next space. So what's the difference between ADAS and autonomous driving? And by the way, this is the picture of the Jaguar Land Rover Robotaxi. They showed this concept about a couple of years ago. On the top, you see a Tesla, a Volkswagen. These are typical vehicles that you would buy. They come with what we call ADAS, right? Advanced Driver Assistance systems. And the robotaxis are not really ADAS, they're autonomous driving. So what's really the difference? The difference here is what SAE, the Society of Automotive Engineers, calls levels of autonomy. Typically, when a human driver is driving the vehicle and there is absolutely no automation in the vehicle, we call that level 0 automation. The vehicle may give you some warnings about, there's a pedestrian, you're about to hit another vehicle. It can give you signals, it can give you visual and audio warnings, but it doesn't do anything to stop you from making a mistake. The human is still completely in charge. So when you do that, it's level 0 autonomy. Level 1 autonomy is one of the two things: either longitudinal control, which is accelerate, slow down, brake, or lateral control, which is turn left, turn right, make lane changes. One of those two will be done by the vehicle, while the other one will be done by the human driver. So that is, just one of these controls, which basically means adaptive cruise control, a feature where the car drives itself and slows down if the car in front of it slows down. That can be a level 1 feature. Or lane centering could be a level 1 feature. Level 2 feature is if both longitudinal and lateral control are applied by the vehicle and the driver is still in charge. They will supervise. If the vehicle makes a mistake, the driver has to intervene and take over. So until these 2-3 levels, the vehicle is not completely in charge. The driver is still in charge. So that is what we typically call ADAS. It's a driver assistance. The driver is still in charge. They're there. And if there is a mistake, the driver is responsible. The vehicle is not responsible. So that's typically what we call ADAS. When we get into the next levels where the driver starts disengaging more and more and more, the vehicle is more and more in charge, and the driver may have certain circumstances at level 3 to intervene and say, hey, the vehicle it drove about 80% of the way, but 20% of the way it made a mistake, I need to take over. So that's the scenario where the driver still might have to take over. Versus at level 4, that's not even the case. The driver cannot take over and doesn't have to. The vehicle is completely in charge. If the vehicle makes a mistake, it just comes to a stop, or it needs to figure out how to recover from that mistake. And at level 4, you can say what conditions under which that vehicle can be autonomous. We can say, hey, if it snows, the vehicle will no longer be autonomous. Things like that are acceptable because you define the ODD. Versus level 5 is full automation. Literally, there are no restrictions. The vehicle will do autonomy anytime, anywhere, under any conditions. So level 5 autonomy is like 20, 30 years away, very easily. Most of what you see in robotaxis, deliveries, trucks, etc., is level 4, where the vehicle, it can make mistakes. There is no driver to take over, but when it makes a mistake, it can recover or come to a stop. And there's a recovery mechanism for it. So those are the levels. And if you look at 3, 4, 5, those are autonomous driving. 0, 1, and 2, it's ADAS. And usually level 0, 1, 2 features are deployed in vehicles that we can buy. Emergency braking, adaptive cruise control, lane center control, features like that, and warnings when you are about to run into something, collision warning, things like that as well. The US NHTSA, the National Highway Traffic Safety Administration, has various classifications, what they call the various eras of safety. From 1950 to 2000, safety really meant the vehicle has cruise control, seat belts, anti-lock brakes. It's not autonomous. 2000 to 2010, you started adding some level of electronics to it. Electronic stability control, blind spot detection using radars, maybe ultrasound, forward collision warning using radars, lane departure warning, possibly using cameras or even radars. Those kinds of things, just some electronics, mostly radio waves, was the next era of safety. And the third is where we started getting more into vision, right? We started using cameras to say, let's use rear view video systems, AEB, emergency braking, detecting pedestrians and applying the brake, and lots of different features, including lane centering and cross traffic alert. So now you're using multiple sensors, radar, camera, etc., and you're taking more intelligent action. From 2016 to 25, we're now very focused on partially automated safety, going to level 2, level 2.5 to 3, where the traffic jam assist is where the driver can basically disengage and read a book. But if the vehicle needs the driver's attention, it will raise an alarm and the driver needs to take over. So lots of features that are being worked on at the level 2.5, level 3. And we are expecting 2025 plus for full autonomy with full highway autopilot or even urban driving. So the vehicle can completely drive itself. The driver may or may not need to disengage. So those are the classifications that NHTSA has. Any questions until this point?
So there is a question from Angeline speaking. In case of sudden natural disaster, can a person who is traveling in the autonomous car escape from the car? Is it possible to handle the car manually in the case of the autonomous car shuts down, they escape from the disaster?
It's a yes and a no. They cannot drive the car, but there are mechanisms very clearly to alert. So usually in a robotaxi, you're monitored. There's a CCTV that's being monitored, and there is usually a button to raise alarm to call an operator and say, hey, my vehicle is stuck. And obviously, if the vehicle is stuck due to any issues, they would already get a notification from the vehicle. So the vehicles tend to be intelligent. And of course, if you need to escape from the vehicle, you can obviously escape. There's an emergency exit and things like that. So there's various safety mechanisms. Even if a vehicle comes to a stop during any particular situation, the user should be able to exit if it is safe, or the best course of action might just be stay inside the vehicle and alert the operator. All these different areas are also being worked on.
Sir, another question from our faculty, David Priya. Sir, can you explain more about the truck platooning, like the separation, the distance between the vehicles? So, what should be the minimum separation between the vehicles? Like that, some technical details. Can you give more information?
Yes, so typically ACC, adaptive cruise control, is where that separation distance comes into the mix. There are three levels usually. 1 second to collision, 2 seconds to collision, 3 seconds to collision, right? Those are the three levels. And usually the user, the driver, in an ADAS system, I can set what should be the collision time. And that determines the distance, and that distance depends on how fast I'm going. So we go back to this question of I detect that the vehicle in front of me is coming to a stop, and I need to apply the brake, and there is only 1 second between myself and that vehicle before I collide into that vehicle, which means I need to be able to detect that faster, come to a complete stop much, much faster, right? So that means the response time of that system needs to be good, and there's a response time of your brakes, and that also depends on the weight of your vehicle. So lots of different parameters go into that mix. So this is going to be a different answer. The distance depends on your speed and your weight, and usually the constant that we maintain is the time. And that time constant, and depending on all your dynamics of the vehicle, your question is how much distance do you need to maintain and how much do you need to apply the brake to come to a complete stop on your particular vehicle. Very interesting problem, but that solution is different for different vehicles.
Okay, this is a question from Raja Gopalan. China has deployed autonomous ships in its coast guard and developing autonomous utility helicopters. We can automate the shipping industry, sir, as it is not much complicated. Are there any initiative done to build an autonomous ship, sir?
Yes, there are. There are many US companies as well being able to automate shipping. It probably is a very it's not very advanced, not as advanced as cars, because today shipping is already expensive, and kind of the human labor cost is probably lower compared to the overall benefit of the ship. So autonomy is not very heavily used. So at least the pressure to bring autonomy is not that high. But yes, there are many startups that work in that as well. And of course, autonomous helicopters, I mean, the whole autonomous drones and people movers, being able to move people in autonomous drones. You can go to your work from your home in an autonomous drone. So that's another field that's coming up as well. Many startups in that space as well.
Okay, sir.
Okay, we can go to the next set of slides. So all the technologies, hardware, software, lots of different things that come together. It's a crazy space. Lots of new developments coming up. But basically, the functional blocks in an autonomous driving system. Most of you might be familiar with this. The perception part, where the vehicle sees and senses what's around it, and really figures out where am I, what's around me, and what do I make of that. Sensing, sensor fusion, object detection, classification, and semantic segmentation are the features that you typically implement. You use the sensors like cameras, radars, lidars, ultrasound, and many other possibly different kinds of hybrid sensors. And the techniques you use are computer vision, image processing, machine, and deep learning. So typically the whole idea is when you complete the perception step, the vehicle has a complete awareness of where it is, or at least what's around it. So what's my environment? Who are the actors in that environment? So now localization is where the vehicle locates itself in relation to its environment. So where am I on this road, and relative to all the obstacles around me, and how far am I from the obstacles that I'm going to potentially go hit? So things like that. We use vehicle positioning, we use mapping, we use sensors like GNSS, IMUs, inertial measurement units, wheel ticks, HD maps, or even SD maps, visual positioning, using cameras to really estimate your distance to all the surroundings, and having maps to tell you what that surrounding should look like, and lidars as well, using the point clouds. So you use techniques like occupancy grids, odometry, Kalman filters, particle filters, simultaneous localization and mapping, slam. So lots of different techniques to really say, okay, the vehicle at this point is very certain where exactly it is in respect to its environment. Then the third part is the path planning. So now that I know where I am and who's around me, how do I get to my destination? There's the mission planning part, there's the behavior planning, local path planning, and velocity profile generation. How do I speed up? How do I slow down? Things like that. Again, the techniques being used: occupancy grids, finite state machines, road network graph, path prediction, shortest path search, time to collision, collision checking, map tracking, trajectory propagation. So at the end of this, you really know where you want to go. What are the next steps to take? An important element here is, what are the surrounding objects going to do? How are they going to behave? Is a pedestrian going to walk in my path? Is another vehicle going to come in my path? So kind of trying to predict what the other one is going to do. Object tracking, behavior prediction, motion prediction, and trajectory tracking. So you want to, even though right now everything is clear in front of you, you could have a vehicle that's coming at you right now that could hit you, right? So you want to predict where that vehicle is going. The final path is using every bit of information you've got. You apply the brakes, the accelerator, the steering to say, okay, let's go in this direction. That's a control function. And definitely some of you might be familiar with it, especially on the mechanical side. Kinematic modeling, dynamic modeling, vehicle dynamics, PID control, model predictive control, etc. So really, these are the technologies that a typical system has. And of course, it's different for a robotaxi versus truck, versus ADAS system versus autonomous trucking driving system. Different vehicles, different dynamics. But overall, these are the functional blocks that make an autonomous driving system. Any questions on this part?
Sir, what are the infrastructure requirements for these autonomous vehicles regarding the roads?
Yes. So the road surface, effectively, let's look at longitudinal and lateral, right? For longitudinal control, the vehicle typically uses sensors that detect, how far is my obstacle from me, or is there an obstacle at all? So in the absence of an obstacle, all I'm going to do is just keep going straight. And if I see an obstacle, I'm going to either slow down or stop. So that typically is about, the road infrastructure you need is traffic signals, stop signs, any other signs that are important, like including speed limit signs, because the vehicle sees and says, okay, the speed limit is 50 miles per hour. I'm going to slow down to 50 miles per hour, things like that. So that's important. With respect to lateral control, the lane markers are the most important part, where the vehicle has to stay within its lane, which means that the left and the right lane markers have to be very clear, and the vehicle can stick to that. So usually that's the need, because it uses vision. You want to give it enough markers to say lateral and longitudinal control are foolproof.
Another question is from Rahul. Apart from those you mentioned, are there more sensors for better performance? And kindly discuss about the processors used to build these kind of vehicles.
Absolutely. The very next slide is on the sensors. I'll get to that in just a moment.
Okay, sir. Right now there are no more questions.
Okay, great. We can get to
Sir, one question. This is from Venkatesan. Sir, in India, the roads are not perfect like there are many potholes. How will the cars handle this?
Well, potholes are not the problem. The lane markers are the problem, right? Because for lateral control, you would need to make sure that there are lane markers. So yes, that is a problem that needs to be solvable. It needs to be solved, and it is solvable, right? It's purely a matter of, in the road that is designated for autonomous driving, or in the zone that's designated for autonomous driving, you just want to use a lot more paint. That's all it is. So that's where the infrastructure support needs to come in.
Okay, sir.
Great. So we'll get into sensors. Typically, as I mentioned, an autonomous vehicle or even an ADAS system has cameras, radar, and in sort of more expensive vehicles, you have LiDAR. Cameras, yeah, most vehicles today, the more advanced luxury vehicles today, even in the passenger car segment, can have up to 10 cameras, maybe even 12 cameras, because you want to have 360-degree view around the vehicle. And much of the labor is being done by the front camera. So there can be even 2 or 3 front cameras with different fields of view and different resolutions, even sometimes, where you will be able. I mean, most of adaptive cruise control, emergency braking, lane center control features like that are mostly a function of the front camera. So, but when you're trying to make an automatic lane change, for example, you want to see to the side to make sure no other vehicle is coming at you. So that's where the side cameras start coming in. So a typical Tesla, I believe, has about 8 cameras, and some of the more technologically advanced Chinese companies, they have 12 cameras, very high resolution, 8 megapixel cameras, and so on. Radar is kind of on its way out. In fact, the principle behind sensors is you don't want to rely on one sensor. You want to have more than one sensor. You need the redundancy. You need at least 2 sensors telling you the same information. That could be camera and radar. It could be multiple cameras. It could be camera and radar and LiDAR, or camera and LiDAR, any combination of these. So if you're just relying on one camera, you could be making mistakes. If you have more than one camera one sensor telling you the same thing, then you're not making as many mistakes. So that's the principle. Typically, cameras are 360 degrees around the vehicle. Radars, there could be about 5 in a passenger vehicle, 1 in the front, 4 in the corners. And LiDAR, since it's still expensive, it could still be about $1,000. There's usually one LiDAR in a passenger vehicle, but there's a lot of LiDARs in a Robotaxi because cost is not a factor for a Robotaxi. And much of the computing that we do today on autonomous vehicles, NVIDIA is very much the leader in that space. Very high performance computing particularly for deep learning. NVIDIA has a chip now called Orin X, which is going to launch in about a year from now. So that's the most advanced chip that most companies are using today. And Intel, they used to be a very strong player, but not anymore, not as much. Mobileye, which is a division of Intel, it's very useful in ADAS situations because they're a very inexpensive camera-based solution. But for full autonomy, for more flexible development, most OEMs seem to like NVIDIA. But NVIDIA has more of a problem with their performance is good, but their power consumption is very, very high. So that's where some of the application-specific integrated circuits for deep learning and neural network inference. So those are becoming much more popular because they can give you more trillion operations per second, more TOPS per watt of power. So power consumption is very important, even particularly in an electric car. So there's now an interest to move towards lower powered systems, and NVIDIA has a very high powered system. And you can see how much data gets generated around all these sensors. So it's not exactly this particular vehicle. This is a Waymo vehicle, Jaguar E-Pace, I believe, if the name is correct. And you could see there's various sensors around this vehicle. Waymo puts these sensors. They buy a Jaguar vehicle and they put the sensors. They call that building a kit on that vehicle. But look at the data. There's like 4 terabytes of data generated by a typical autonomous vehicle in a given day. So that's a lot of data to process, lots of data to collect. So designing that data flow inside the vehicle, making sure you're not losing any packets, itself is a huge problem. It's a huge engineering problem. And then being able to get that all at the lowest cost possible into a cloud infrastructure and being able to process that. It's a very, very large problem many companies are looking to solve and still solving. It's not completely solved yet. Now, it's not just about sensors and computing and all that. In autonomous vehicles, you're dealing with a lot of data opportunities. Think about this vehicle is going around a city. It's got cameras looking at every angle, radars, LiDARs looking at every angle. So these sensors are giving you lots of data. And there are people sitting inside these robotaxis. Those people are doing things, right? They're consuming content. They're looking at applications. They're doing things. that could be very, very valuable data for us to say, okay, this is what they like. They would like to watch this movie, or they like to play with this game, things like that. So that's a lot of behavioral information you can collect when someone's sitting inside an autonomous vehicle. And the vehicle itself is giving you so much performance data from the engine, the motor, the battery, and so on. And overall environment. We were talking about potholes a moment ago, but this vehicle, let's think about a taxi just driving around your city. It can see every pothole there's on the road, right? A typical way a city tries to find and fix potholes is to, they drive around, people drive around and say, hey, there's a pothole, we need to fill that. So manual work was being done by the city, and that was costly to find every pothole, and that's a big problem. Versus now what you can do is let's think of, there's 10,000 GM vehicles with cameras driving around that city, owned by many different people. These cameras are all looking at every pothole in the city anyway. So what happens if GM were to look at all that camera feed, use big data to detect potholes, and with GPS location, send it to the city management saying, here are the potholes in your city. That data is valuable in terms of money, right? The GM can literally charge money from the city saying, hey, per pothole, I'll charge you $10. And the city will still be saving a lot of money. So it's huge. From the data opportunity, data mining opportunity, it's huge. And it actually makes us more productive. The city doesn't have to hire 100 people to go drive around looking for potholes. So very, very interesting convergence of data science, big data, and autonomous vehicles. And this is not even looking at any autonomous algorithms. It's just purely the amount of data that comes out of the vehicle. And go back to this last mile delivery, the same problem in a different context. In my neighborhood, there's like 50 Amazon trucks that come in every day. They can do a lot of analysis of my neighborhood, right? What are the traffic patterns? What do houses look like? What do the potholes look like? What does the landscaping look like? Is anybody using too much water? There's a lot of information they can gather, and that information is very, very valuable. And also think about if you are doing a fleet like a FedEx fleet, the management of the fleet is a big computer science problem. You have to have communication, you have to have data, you have to be able to figure out where every vehicle is at any point in time, how much fuel they're using, how can you optimize the fuel, is the driver driving safely, lots of different variables there. And the logistics of, what is a more optimal path to send these vehicles on? And are all these vehicles, is anyone going to break down? If it breaks down, it's very, very, there's a lot of money lost by the company. Predictive maintenance is huge as well. A vehicle needs to tell you that it's going to fail before it fails. So that's a huge, huge, huge development space as well. So smart cities are all about this, right? Being able to collect data from every single possible sensor, every single possible aspect of the city, but using it to fix problems much, much faster at a much lower cost. So there's a lot of opportunity in this space as well, using autonomous vehicles. Connectivity, in the interest of time, I'll just jump into this really fast. There's lots of focus on doing more connectivity computing on the edge, inside the vehicle, using maps, traffic data, doing more computing on the cloud. And then there's these what we call V2X, vehicle to vehicle, vehicle to infrastructure, vehicle to pedestrian communication. So instead of you driving around or in an intersection, there's someone crossing the intersection. The vehicle's camera has to see them and say, hey, that's a pedestrian. I should not hit them. Hit the brake, and hopefully you come to a stop before you hit them. So it could be error prone. Versus what happens if the pedestrian's phone and the vehicle communicate with each other and with the traffic light as well. And the traffic light actually tells the vehicle, hey, you know what? There's a person crossing the road right now. You should slow down because you're coming to that intersection. And the person's phone is used to locate that person, and that person is crossing right in front of you. So the vehicle can slow down and come to a stop. So that communication, vehicle to everything, is a huge area of development as well. It's very much in the infancy. It's still very much theory, no major standards. It's all still being worked on. So it's not just, just autonomy in terms of the connected electric vehicle ecosystem. The CASE, Connected Autonomous Shared Electric Vehicle Ecosystem, is a huge opportunity in terms of IoT applications, in terms of data, in terms of intelligence, lots of different areas. So if you're in any discipline of engineering, autonomous vehicles have a lot for you. But it's not just about the autonomous algorithm, but it's about the applications of everything that an autonomous vehicle brings to your world. So with that, I'll move towards a wrap up. So I was, just for fun, Googling what an Apple car looks like. So these are not the real Apple car. Apple's car design is still secret, but many different people have different views of how an Apple car looks. These are all just renderings by private individuals. But everyone's got a really cool idea about what an Apple car is, right? You want to see what a real Apple car looks like today? That's what it is. So these are just autonomous vehicles, a Lexus that Apple bought, and this is believed to be an Apple vehicle, as in Apple bought this Lexus, and they put the kit on top of it, lots of cameras, LiDARs, as you can see, and they're driving it around to test their autonomous algorithms. So what it really indicates to you is that autonomous is not all about these cool looking vehicles. There's a lot of work to be done. And if you come to San Francisco, you'll see many of these vehicles from different companies driving around. It's a lot of work. Like I said, 100 people in Tesla are developing algorithms, but the remaining 200 people are just annotating data. So it's so much hard work, but it's a very interesting space. I mean, I got into it by accident, and I'm definitely having a lot of fun learning a lot of new technologies. So I'm definitely hoping you would be able to, you'd get curious enough to look into this even more and learn more. And hopefully some of you will make this your career as well. There's lots of opportunities. So autonomous driving, as I mentioned, is at the intersection point of many computing and software technologies, not just that, even mechanical, any branch of engineering you are in, there's something in autonomous driving for you. And there's some areas where you can definitely impact. But we are still in the very early stages of autonomous driving. All these slides I showed you, as advanced as they are, I think there's a lot more to be done in autonomous. So we're still at the very, very early stages. There's many, many years of work that's left to be done. So the best is yet to come. And there's a lot of opportunities for you over the next several years. I think you can make it a career for the rest of your life. This world just really started with some guy saying, hey, why couldn't my car drive itself? So Steve Jobs' quote, I really like this one. The ones who are crazy enough to think they can change the world are usually the ones who do. So, some of you, I hope, are crazy enough to try this space and really, learn more and contribute to it. With that, I'll wrap up. Thank you very much.
Any questions? The participants, students? There was one question posted by Rahul. Could we implement these autonomous feature in emergency vehicles such as ambulances, fire trucks, etc.?
Yes, you can. You can very well do that. Today, one thing is, ambulance drivers and fire truck drivers, they have to be daredevils, right? Because you have to just kind of weave through traffic to save somebody's life. And you cannot be too careful. You've got to be very daredevil. Autonomous vehicles are extremely careful. They are very, very hesitant. So that's the only reason why you probably cannot use autonomous vehicles for this application, because sometimes you just have to drive through traffic and get things done. But other than that, in terms of the application itself, why not? It's a vehicle, it can drive itself. So even an emergency vehicle can still be autonomous. And to go to that point, there are applications where, like, mining trucks and, mining robots, stuff like that, where it's dangerous for a human to be in. And those applications can be done by autonomous vehicles. And that is being done today as well.
Sir, Raja Gopalan has posted a question that is on the downside. With all these devices keeping a close eye on our daily activities and collecting much data, there will be no privacy to anyone in the future, or it is becoming like a surveillance state like China, but here private companies are doing it. So that is a big disadvantage of these technologies, sir. So is it really a drawback?
Well, it depends, right? it depends on which side of the spectrum you are in. It all depends on you as an individual. There are a lot of us who give a lot of our information to those social networks. We know that, and when we do that, privacy is not that important to us. And I mean, this can get very annoying, right? I go to Google and I search for something, and then the next time I go to Facebook, Facebook shows me an ad for that thing, right? So things like that are happening now. Privacy is at a premium today. But if you do want to protect your privacy, these are all opt-in services, meaning if I don't want to give you my data, I don't want to give you my data. But that said, this is all about, I mean, smart devices and smart applications are all about, if you give data, we'll give you a better experience. So that's what many of these companies take advantage of, right? Including the Facebooks of the world, including your smartphones. That's what they do. I mean, they track your location, and with that location, they can tell you where you can find a good deal on food or groceries or things like that. So it's a trade-off. But most of the time, the governments in some countries are taking this very seriously. Yes, it is extremely intrusive. So European Union, for example, makes it very stringent. You have to make sure that the user really consents to their data being used before you can collect it. So things like that. But of course, in countries like China, that's not the case. You have to collect data and give that data to the government as well. So different countries have different approaches.
So another question from Venkatesan. What happens if there is a malfunction in the middle of the road while driving? How does an autonomous car handle that?
A robotaxi or any autonomous vehicle, if it is connected, it basically sends a distress message. It comes to a stop, it pulls over. You have enough redundancy built into the system to say, okay, don't stop in the middle of the road, come to the side of the road, pull over, and then send a distress signal saying, okay, something went wrong. Possibly you can send information because it's collecting all this data, right? It tells you, okay, you know what, I have a flat tire or I have an engine problem, whatever the problem is. It collects all the diagnostic data, sends it out to the control center, and the control center can figure out how to solve that problem and bring that vehicle back to life. If they have to tow the vehicle, they send the vehicle to tow. So yes, all that is, it's not so much part of the autonomy algorithm, it's really part of the connectivity. So that all those applications are being developed as well.
So, what about the accident rate of these autonomous vehicles?
It's, well, there are two different answers to that. Statistically speaking, there is a certain number, which is like several billion miles. You are allowed to have an accident, one accident in several billion miles. Only then will you be an autonomous vehicle be as safe as a human driver, because they're basically looking at how many miles all humans are driving, and how many accidents do they have. Divide the two numbers and say you're allowed to have one accident per so many billion miles. But that's not a good metric, right? Some humans, they can have an accident every 10 miles, and some humans never have an accident. So it really is more of a statistical exercise. But how do you really prove that an autonomous vehicle is safe? It goes down to, I mean, there's no perfect metric. California DMV used to measure this as number of disengagements, but disengagement is not a perfect metric. It's really about how close to an accident scenario does a vehicle get before the driver has to intervene. One company that's collecting very good information is Tesla. They have something called shadow mode, right? It's not really autonomous, but it's running an autonomous algorithm while you are driving. And it says, okay, hey, everything that the driver is doing, I'm also doing. But at a certain point, if you, the driver, does something different from what the algorithm is doing, that's either your mistake or the algorithm's mistake. So those disagreements, they do measure. So that tells them a very, very good measure of how reliable their autonomous system is. So if the disagreements are for a good reason, then their system is good. If the disagreements are for a bad reason, they learn, fix, and then they do their numbers. So ultimately, there's no right answer to it. But in a particular scenario, if the vehicle is basically accident-free in a given ODD, then you can say it's safer than a human being.
So as there is no drivers, who is liable for accidents? Who will be responsible for that?
That is still being figured out, mostly by the lawyers. I mean, the typical mechanism that happens is the vehicle is liable, as in the company that owns the vehicle is liable, but they are collecting enough data to say what went wrong. So if what went wrong is really in the autonomous algorithm, then the liability can shift to the company that wrote the algorithm. So what that mechanism, it's not perfect yet, but it's really very subjective. It's being worked on.
Yes, sir. Thank you very much. Really, this webinar is very interesting and more informative. And really, the students will will have some interest now to work on these autonomous vehicles. So, suppose if they want to study more on these autonomous vehicles, what are the courses they can do further?
Yeah, there are two things that I would generally recommend. There is a University of Toronto autonomous vehicles or self-driving vehicles course on Coursera. That's a good one, and it's actually not very expensive. It's about $45, I believe, per course, and there are 4 courses, so it's not that expensive. And there's obviously the Udacity program for, I mean, it's a nano degree for autonomous driving as well. That's probably more expensive than the Coursera one. I would definitely say the Coursera one, I did take it, and it's pretty interesting, and it gives you a lot of the basics.
Okay. Okay, sir. Thank you for sparing your time with us. So now I request Mr. Venkatesan, the Assistant Professor, PC Department, to deliver the vote of thanks.
Yes, sir. Thank you very much, sir, for giving me the opportunity. Good morning, all. As all good things come to an end, so is this lecture. On behalf of St. Joseph's College of Engineering, I take this opportunity to propose vote of thanks to those who have directly and indirectly contributed to this guest lecture series on trends and opportunities in autonomous vehicle, organized by our Department of Electronics and Communication Engineering. At the outset, I thank our chief guest and research speaker, Mr. Shyam Sundar, Senior Director, IAI Product Management, Los Angeles. Sir, we are really enlightened with your knowledge and presence. Thank you very much for sharing your knowledge. We are also thankful to our Honorable Chairman, sir, Managing Director, Madam, and Director, sir, for their motivation. I would like to thank our Principal, sir, and HOD, Madam, for their enthusiastic support. A special thanks to organizing committee and teaching staff members for their unflinching support and coordination. For a heartfelt thanks to our students for active participation. With these warm words and a kind message, move to end of the today's guest lecture series. Thank you very much, sir.
Great, thank you very much. Thanks for having me, and stay safe, everyone.
Thank you, sir.
Thank you.
Thank you, sir. Thank you very much, sir.
Thank you, sir. Madam, Elin, madam. Akalia, madam.
Sir?
Thank you, madam.
Thank you, sir.
Thank you, sir. Thank you, sir.
Thank you, madam.
நல்லா இருந்தது சார் செஷன்.
நல்லா இருந்துச்சு மேடம். இவர் ஆக்சுவலா நான் ஒரு எம்டிபிக்கு போயிருந்தேன். ஒரு வெபினார் இதுல பிஎஸ்சில பண்ணாங்க. அங்க சேம் டாக் அவர் கொடுத்தாரு.
ஓகே ஓகே.
நல்லா இருந்துச்சு. அதனால தான் திரும்ப இங்க நம்ம ஸ்டூடெண்ட்ஸ் பண்ணலாம் அப்படின்ட்டு பிளான் பண்ணிட்டு.
ரொம்பவே நல்லா இருந்துச்சு. ஸ்டூடெண்ட்ஸ்க்கும் நல்லா இன்டராக்டிவா
ஆமா. ஓகே மேடம், தேங்க் யூ.
சார் தேங்க் யூ.
Thank you, madam. Venkatesan?
Sir?
Thank you.
Thank you, sir. Thank you very much, sir. Thank you, sir.
Priya,
Thank you,
Jasmine,
sir.
Jasmine, thank you.
Thank you, sir.
Thank you.